Hello and welcome to our lesson on the real numbers. So we're just basically going to be classifying. When you're looking at a number, you should be able to identify what type of number it is or what classifications it belongs to. And the set of real numbers is almost the top of what we call the number classification system, or if you want to think about it as like a number food chain, it's almost the top. We will talk about what the top is a little later on. But for now, what is a real number? Okay, that's just about every number we know. Any number that can be plotted on a number line, can be classified as a real number. And the abbreviation for the real numbers is a capital R, and sometimes you'll see it with a little extra line through it. So that abbreviation R can be used to identify the set of real numbers. So I've got a number line here. Obviously the numbers that are labeled on the number line have to be real numbers, but anything in between these numbers I've labeled and anything after, right, these numbers are going to go on forever in both directions. They're going to go on forever toward positive infinity in this direction and forever toward negative infinity in the other direction, and again anything between. So for example, I could put in the square root of 3. So the square root of 3, that's approximately 1.7-ish, would be like in here. So the square root of 3, it's about 1.7. I could plot that on a number line. That's going to be a real number. Or maybe like negative 3.5. Negative 3.5 is a decimal that's right in between negative 3 and 4, so that's going to be a real number. I can plot that on a number line. How about something like 4.3 repeating. 4.3 repeating. That's going to be over here somewhere. So 4.3 repeating a little after the 4. I could put that on a number line. Right? Anything that I could squeeze in here. Let's do another one. How about like a half? I could plot that on my number line. Okay, anything that I can plot on there in between these numbers or past these numbers is going to be a real number. Okay, so almost every number we know is a real number. Now the subsets are a little trickier because they're a little more distinct. So some subsets of the real numbers. Well, the set of real numbers basically breaks into two major subsets. So all of our real numbers are numbers that we can either write as fractions or we can't. So the rational numbers are the real numbers that we can write as fractions. Now there's an abbreviation for rational numbers. We can't use R again, so powers that be, not me, powers that be said, let's use Q to identify the rational numbers. So if we want to abbreviate rationals, we'll call them Q. And again, the other subset we call the irrational numbers. So all of our reals are going to break into one of those two categories. All of our real numbers are either rational or irrational. A real number is rational if it can be written as a fraction. If we can make an exact fraction out of it, then it's going to be rational. And if we can't, then we're going to see it as a non-repeating, non-terminating decimal. That's going to be our irrational number. And the irrationals have an abbreviation as well, I forgot to mention. That's going to be an I. That one makes sense, just like the R for real makes a sense. Okay? So rational numbers, again, anything we can write as a fraction. For instance, 3. 3 I can make a fraction by putting a 1 under it, or like 0.75. I can definitely make 0.75 a fraction. Let me make this list look a little nicer. I can make 3 a fraction, we said, by putting a 1 under it. Or 0.75, hopefully we realize that's 3/4 as a fraction. So that's definitely rational. 0. Going color crazy here. 0, I can make a fraction just like the 3 by putting a 1 under it. So we're going to call that rational. 0.3 repeating, that's one I put up there a second ago. That's still a rational number. If you didn't know, the fraction 1/3, you could use your calculator so I could show you here. 1 divided by 3, that's 0.3 repeating. There's an exact fraction for that. So that's going to be rational. Negatives, like -4, totally fine. Again, I could put a 1 into that and make that a fraction. Anything we can write as a fraction is going to be rational. However, there are some real numbers that are those non-repeating, non-terminating decimals, like the square root of 3. That's going to be an irrational. We saw that in the calculator, square root of 3. That decimal goes on forever without any pattern or repetition. And so let's say the square root of 3 is approximately We're going to go 1.732, 1.732, and then let's put a little dot, dot, dot. I don't really know what's happening next. I mean, I got a few digits, but at the end of that, I have no idea. Another common irrational number we see is pi. So pi we know is about 3.14, but technically the decimal is going to go on forever. And again, I can show you in here. Let's put pi in there. So 3.14159265359. I'm just going to keep going without any pattern. Okay, so those are irrationals because there's no exact fraction for it. The decimal goes on forever without that pattern. Okay, now we have some subsets of the rational numbers as well, and I'll get one big picture to put this all together in a minute. So we have these real numbers we can plot in the number line. Some of them we can write as fractions and some of them we can't. If we take that group that we can write as fractions, we can divide that group into some smaller groups, some smaller subsets. So in that group of rationals, again, the ones that we can write as fractions, so we're dealing on this group right now. If we took that group and got actually rid of the numbers in there that aren't whole, if we're just looking at the positive and negative whole numbers, so no actual fractions or decimals, just the positive and negative wholes from that group, we have a subset of the rationals that we call the integers. And to abbreviate the integers, what do we get? Z. Well, we can't use I because we already used that for irrational, so the powers that be said, well, let's call it Z. Okay? Now, if we took the positive and negative whole numbers and we cut off the negatives, we just started at 0 and went from there, the positive whole numbers and 0, we actually call those whole numbers. So those are the whole numbers, and we can use a W to abbreviate that group. So the integers are like -3, -2, -1, 0, 1, 2, 3, and we go forever in both directions there, but no fractions or decimals, just those positive and negative wholes. The whole numbers, we get rid of the negatives from the integer group. So we're looking at 0, 1, 2, 3, 4, and so on, just forever in the one direction. And then if we take the whole number group and we get rid of the 0, we have our last little subset, which we call the counting numbers or the natural numbers. Okay, the natural numbers, n. So again, that starts the whole number, or after 0 from our whole number group. So the counting numbers. If I said to start counting, you're going to start at 1, right? That's where the natural numbers start. Okay? Those are all the different ways we can classify our real numbers. And so you can better see how these all connect, we're going to make a little visual representation here. So the largest circle, that's our big group, we said the real numbers. Okay? So all of our real numbers break into two subcategories. Some of the real numbers we said we can write as fractions, and we're going to call those rational. And some of the real numbers we cannot write as fractions, we're going to call those irrational. Now there are no subgroups of the irrationals, but there are subgroups of the rationals. If we take the positive and negative rational numbers, we have the integers. If we take 0 and the positive integers, we have the whole numbers. And if we take the whole numbers after 0, we have the last little subgroup, which are the natural numbers. Okay? So these are whole numbers, and these are natural numbers. And numbers. And integers, okay. Integers is the only one I have to say numbers after. We're not going to say integers, numbers. So just integers. So just, again, so you can get a feel for this, or how this picture works. Like, natural numbers are a subgroup of the whole numbers. So you see how this natural circle is completely inside the whole number circle? It's because all natural numbers are whole numbers. And they are also all integers, right? And all whole numbers are integers, and all of them are part of the rational group. These circles are fully enveloped because all of those numbers belong to that larger group, okay? So that sort of works outward here. So every natural number has to be a whole number, integer, rational, and real. Or every whole number has to also be an integer, rational, and real. Or every integer is also rational and real. Or every rational has to be real. And every irrational is real as well. Okay, so you can see the connections. And now, just a couple questions to make sure we're good here. If I said every natural number is a whole number, is that true or false? Well, every natural number Again, every natural number in that whole number circle, yes, is true. Every natural number is a whole number. That's a true statement. But if we said that in reverse, is every whole number a natural number? This is false. There is specifically one whole number that is not natural, and that is the number 0. 0 is whole, but not natural. It seems funny to say that say it like that if you're thinking about just grammar. I want to try to fit this a little bit better. Sorry. This is false. Okay, 0 is whole, but not natural. Okay. Now, you should be able to classify any number I give you as well. So if I said to classify, for example, 0.62, what I mean is tell me what groups of numbers or which ones of these classes it belongs to. So 0.62 is definitely a real number. Right? Anything we could plot on a number line is a real number. So we're going to say this is real, and I'm going to use the abbreviation. Now, is it rational or is it irrational? That'd be the next place to go. Can we write it as a fraction or can we not? Well, we can. 0.62, if you put that into Desmos, see in blue next to the 0.62, it'll allow you, if it's possible, to take your decimal and make it a fraction. 0.62 is 62 out of 100. It's 62 in the hundredths place of the decimal, and that reduces to 31 out of 50 as a fraction. So in fact, 0.62 has a fractional value. It's 31 over 50. So we know that it's going to be rational, and we were using the letter Q for rational. But it's not going to be integer, whole, or natural because it is a decimal. The integers, wholes, and naturals are all whole. There's no fractions or decimals in any of those subgroups. So it's just a real, and it is rational. -7, again, a real number. I could definitely put that on the number line. It can be written as a fraction. I can stick a 1 under it, so it's going to be rational. It is an integer. That's a negative whole number. So that's going to be an integer, which we call those z. But it won't be a whole number or natural. Those don't have any negatives. Okay? And then classifying the square root of 25. So the square root of 25 actually simplifies. That's just 5. So 5, let's see, that's definitely real. We could put that on a number line. And it's definitely rational. I can write it as a fraction, 5 over 1, so that's Q, it's rational. It's definitely an integer, so integers are z's. It is a whole number, so it's going to be W, and it's a natural number. Okay, this belongs to all of those groups. Now, if we're looking at the square root of 15, the square root of 15, just put that in here so we can see it. That's one of those numbers we can't square root. That's that non-repeating, non-terminating decimal. So it still has a value that we could plot on a number line. It's still going to be real, but it is irrational, non-repeating, non-terminating decimal. Okay? So hopefully you're good classifying those numbers if you need to. All right, last couple things here. Some symbols that we use to work with some real numbers. Inequalities, you'll see those quite often. Like the greater than symbol is an inequality. Greater than symbol looks like that. Less than symbol, flip that around. Greater than or equal to. Greater than or equal to is underlined. Less than or equal to is, again, that's underlined. So sometimes we use those to compare real numbers. And then we also use absolute value symbols. So the absolute values look like this, and you'll have some number in between there. And absolute value is a number's distance from 0. So we often think about absolute value as, oh, it can't be negative, and that's sort of true, but that's because it represents a distance, and distance can't be negative. So like if I said, what's the absolute value of 5, you're going to say 5. If I say, what's the absolute value of -5, it's also 5, because on a number line, here's 0, here's 5, here's -5. Well, it's 5 units away here. It's also 5 units away here. So when I ask you for the absolute value of a number, I'm really asking how far is it from 0 on the number line. So because it's a distance, we end up with a positive result. All right. So we're going to try to use some of those symbols in the next couple of Oops, I don't know if I did there erase. Next couple of little problems here. So use a symbol to make the statement true. So 5 and -1, if we were to compare these two numbers, we would say that 5 is greater than -1. Now technically we could also say greater than or equal to. They're not equal, but either one could happen. So if it's greater or equal, then we're fine. Since greater applies, that symbol still applies as well. Now if we're comparing 0 and 2, 0 is less than 2, but again, we could say less than or equal to because only one of those has to be true. So less than or equal to is going to work. Now if I have 3 and 3, I can say greater than or equal to. So 3 isn't greater than 3, but it is equal. And again, as long as only one of those applies, we're good. So I could also say less than or equal. Now 3 isn't less than 3, but again, it's equal, and only one of those two has to be true. Now in this last part here, we could say the absolute value of 5 is equal to 5 because -5 is 5 units from 0 on the number line. And I could say the absolute value of -8 is equal to +8, again because -8 is 8 units from 0 on the number line. Okay, so you'll have a pretty brief assignment where you're going to classify some numbers and maybe compare using absolute or inequality symbols, or maybe do some evaluating with absolute value symbols. We're getting tongue-tied here at the end. Again, it should be a pretty brief assignment, but if you find yourself struggling or needing some extra help, then by all means, just reach out. All right, guys, till next time, take care.